All right, so running the regression model and getting the results is something that you can easily do and be fine with it. The most important thing is interpreting those results. So we are going to look at how to interpret these very results. But there are some few things to note first. This result here does not give us the confidence interval. You can run this command to get a confidence interval for each parameter estimate. You can do that. And you can find the mean of the residuals to be sure whether it is truly 0. Okay. So you can find the mean of the squared residuals. And this mean of the squared residuals is used to do predictive accuracy. It's actually the mean of the squared residuals is used to determine, just like the R square is used to determine the efficacy, and then the square root as well. Okay? The values, when they are positive, means that they are good. And then you can actually find the ANOVA using this command, find the fitted values. Okay? Remember the original value for the first observation is 160, but here it is 161. This is a predicted or fitted value. You can find the fitted values for each, and then find the mean of the residuals, and if it is 0, that is the expected value of the error. Okay? And the value you see here is 0, which means that it satisfied assumptions of classical linear regression model. You can do some residual plots. Okay, you can do some residual plots like this. This is the first residual plot, or you can have the next couple of plots all to be one by once again using the pa infro. I'll put the plot in a 2x2. So if I run this command, you'll get the results on the far right. You get the plot to be 2x2. Now, these are the residuals. So the first one plots the residuals against the predicted or fitted. The second one looks at the normality of the residuals. And as you can see here, it is using the quantile normal probability plot. If all the dots are seated on it, it means that we are in a good shape. The scale location, all of this, we shall look at them when it comes to diagnostics. But I just want you to know that you can generate the residual plot quickly. But there are some things you can also do. Okay, for example, you can find the average. In fact, there are so many metrics that you can use to determine whether your model is good model or it's not. The commonest one is the R square. We shall interpret the R square data. But there are other ones. Okay, all of these I've done them here. All of this. The residual plot will check for diagnostics. We shall look at that subsequent time. The residual plot will check for heteroscedasticity and autocorrelation. We shall look at that later. I've done all of this in the slides for you. You can also find a different, I've put there, I'm going to run it quickly. You can check it later. The same regression we did, you can find beautiful ones, beautiful results. Okay. So this command, installing this library or this package will help you run this. It's called library J2s. Okay. So when you install and run the J2s, and then do this time, look at the end. You don't do summary, you do sum. Okay. And it can give you multiple results. So just watch how it looks like here. So the beautiful thing about this result is that it gives you precisely exactly what you need. The number of observations are given, the dependent variable is given, the type of regression is mentioned, the S statistic is 0, the R square is 99%, and then each one of these have got the p-values and the confidence interval. Beautiful. It is just an alternative to the one that we did. Okay? And the J2 commands help you. In fact, what we just did was the general regression. I can also run the regression without the intercept. So watch it here. If you look here, you can see that I've run it. The first one, I ran it with P. Okay, but the second one, I brought a 0 plus the P, which means I don't want the intercept to come. When you run this result, you will see that it starts straight from price. The intercept is gone. So that is another way if you don't want to see the intercept. You can also run a robust regression using this robust command. Let me just do that and show you the robust regression. So once you run it, the robust regression here means that it is robust to heteroscedasticity issues. We'll dig more into that later. And then you can also run GLM. I just want you to know that there are multiple models you can run, in this, and this is the GLM. The GLM, one good thing about it is that it will tell you the dependent variable. It will also tell you the pseudo R squared, what is known as Krag-Ola square. In fact, if you check it, it's the same as the one that we have. The McFadden, the Akaike information criterion, the Bayesian information criterion, all of these are given to you. In other words, it uses a maximum likelihood estimation instead of the OLS regression estimation. That's a GLM, the generalized list. And then you can put all your results in a beautiful graph. Guys, this beautiful graph, you can easily take it to your document. Okay. And to do that, you need to install a package and load a package known as Stargazer. Okay. So you load this Stargazer. Okay, so you see, it tells me that there's no package called Stargazer, which means I have not installed it. So you need to go to install here, click install, and then install the Stargazer. Let me just quickly install it. You can do it alongside. Very good. Stargazer has been installed. So now let's activate it. I library it. Stargazer is now sorted. Now we are going to watch here. This is beautiful. We're going to run our normal regression. We're going to run the regression that doesn't have the intercept. We'll run the GLM regression, the generalized list model. And we will rename them as OLS. OLS, no intercept. That's the NI. And then GLM. I'm going to run this. And I want it to keep some specific number. I want it at the bottom. Give us the sample size, the R square, the F test, the log likelihood, the Akaike information criterion, the Bayesian information criteria, the likelihood ratio, the wall test. And if you want more of the statistics, once you come to Stargazer, once you go to the far right side, and then you use your Stargazer, it will tell you other things that you can possibly. So once you click here, okay, it will tell you some of the things that you can bring or not bring. They're all here. So you run that, and then you're going to get a beautiful table. Oh, I missed something. There you go. So now look at this beauty. So on this, let me make it bigger. So on this table, it's been beautifully organized. So if you are doing robustness check, so the first one is OLS, that's model 1. The model 2 is the one without intercept. And the model 3 is the GLM. It tells you the value for each one. It tells you the value for each one. And when there is no need to give you, it does not give you. I don't know why it's excluded this value. The location you are. Oh, okay. So because the urban, the location is just 1. The levels are just 2. Okay? And the dummy is just 1. It gives you both the urban and the rural. So for some of them, you wouldn't need it. For some, you will need it. You have occupation trading, occupation teaching, religion, Christian, religion, Muslim. And you can see that the constant is here, but then the other one didn't bring the constant. That's it. And then at the bottom, you can see that they all show the observations. They all show the R square. Not all of them show it because the GLM doesn't show. Instead of the R squared, the GLM will normally use the log likelihood, the Akaike information, which it shows here. And then the other ones will have the F statistic and all. So you have a beautiful data that R can generate for you, and you can talk about this in your thesis. Or you can talk about it, in your work. Now, if you are critiquing the papers and you realize that in the process of the criticism, you realize that they do not corroborate their work by doing robustness check, indicate it. Indicate it in your critique, because that is part of the marks that you're able to. Look, that paper, I've looked at it billions of times and I know exactly what comes out of that. So it's important that you try and you go with the intention of finding mistakes. Okay, let me just take you to the slides. I'm sure you all have the slides. Emily, the slides I just posted, I gave it to them last week.
No, Doc, they're saying they don't have this one.
They don't have this very one I'm showing.
Yes, Doc. The multiple regression slides.
So the one
last week you gave this. Okay.
What about the one I just posted in the group page?
Doc, in our group page, you posted it in another group, and I put it in our group page, but you said it wasn't for us, so I'm taking it out.
The S9 is not for you. And when I said it wasn't for you, I gave you another one.
Please, let me check.
Guys, can you help her? It's like none of you is talking.
Doc, no, I think we have the old the one that you said is not meant for us. Yeah.
Doc, but I think we have this slide too.
You see how life can be. Some of you say you don't have. Some of you say you have. You see, those who don't check things.
No, please, we don't have the one for the multiple regression. It's only the
Doc, I've commented on it. I've commented on it. It's there.
It's there. It's there. You guys are not very serious at all, honestly, because it was there since Friday, since last week. So I don't really know what multiple things you're all doing that not a single one is able to know that you have it. And then, it's like I've done a wasted job. I've wasted my life.
I think I stated that we had it. I got it. So it's in my library.
This is bad. So, you see, the problem is that you are not really, there are few things on that page, but you are not paying attention, but I should pay attention for you. Next time you tell me that you don't have the notes, I'll minus everybody because you delayed me. Okay, so these are the results for all of them. Are 3 models. Now I've added another model. If you look at the one I have here, you can add multiple models as possible. For example, here I add the multiple regression, the one without the internet, without the constant. We have the robust and then the GLM. So I added robust here. But to add the robust, you need to go and run robust first. Okay. So this is a robust. So if you want, we have only 3 models here. But if you want more, there you go. If you want more, you can install another package known as Hacks Table. Hacks Table. Okay. Now, when you library the Hacks Table, okay, so for this particular laptop, it looks like I've not installed Hacks Table. So once again, you go to packages, you click install, then you install it as fast as you can. And then you run the Hacks Table. That will include this. And now you can see that the model 4 has been added. That is a robust regression. That is a robust regression. You can see for that. So what is the whole point here? In fact, the one I just ran, let me just show you the one I just ran. The first model is the usual one. The second is without the intercept. The third is rather the robust. Take note. The third is rather the robust. So when you come to the results section here, the third one here is the robust regression, and the last one is the GLM. That's why I actually customized it. Okay. That's why in the Stargazer here, I customize it. Okay, multi-regression without the intercept. Then I brought the, so here I didn't bring the robust. So I can rewrite this one here, watch it, include it as number 3, which is a robust regression. Now when it come here, I'll copy this and rename it. I'll put it there, rename it as robust. Just call it robust. And then run all of them again. So let's take it. Do not find, oh, looks like I didn't. Says unrecognized object. Which one is unrecognized? So sometimes the robust doesn't show potential. Let me run this first. Yeah, it looks like the robust is not usually accepted. That's why I had to do that one separately using the HAX table. The Stargazer doesn't allow you to generate the robust. So let's leave that one because this one will work. Oh yeah, you have to delete this first. Yeah, work now. So the robust regression is not usually applied to the Stargazer, but it's rather applied to the HAX table. So there are several kind of ways to bring out your table and all of the results that you. Okay, at this stage, I'm going to go to interpretation. Interpretation. There's several other ones that you can see. See, I have all of this. So let's go to interpretation. That's the most important thing for me. But this is what I will let you also be answering in the exam. So the first thing about interpretation is this. Which regression estimates are significant? Which regression estimates are significant? So let me just maximize the result. In fact, we can go back and use our original regression. But hey, you can also use this one. So why is this one so big like that? It's like I can't even see. Let me zoom out. You need to just zoom out and then get a better, better view. I hope that you guys can see. You see everything. I hope. So let's start with the first question, which is in the slide. Which regression estimates are significant? Which regression estimates are significant? If you want to know whether a particular regression estimate is significant or it's not significant, you've got to use the p-value of that independent variable. Use the p-value. If the p-value is generally less than 5%, it means that the regression estimate is significant. Now, the stars will tell you at what particular level. If something is significant at 5%, it's automatically significant at 10%. If it is significant at 0.01%, it's automatically significant at 0.1%. And if it is so, it's also significant at 1%, and 5%, and 10%. So the key point is check the p-value. Now, in this very result, the p-values are not provided. So you got to use the stars to determine whether it's significant and at what percent. So as an example, I'll just take one example. If you take price, you have been told that price has a what? Star. Not 2 stars, but 1 star. And the footnote or the note at the bottom will tell you the implication. So who can tell us what does a star for price mean regarding the significance or insignificance for price? Who can tell us? Price. Is it significant or insignificant? And if it is, at what percent? At what level? What percentage level? Can you guys hear me?
Yes, Doc, we can hear you.
Yes, certainly.
Doc, please say significant at 10%.
How did you know that?
Okay, so if I look at where you've highlighted, you can see that 1 star is when the p-value is less than 0.1, which is 10%. 2 stars is when it's less than 0.05, which is 5%. And then 3 star is when it's less than 0.01%, which is 0.1%.
And so?
And so we can conclude that price is significant at 10%.
Good. Who doesn't understand? Who doesn't get it? Very good. So now, you can tell me complement price, C. What would you say about the significance or insignificance? Who can address for complements? Complement. Yes, Richard.
Yes. Okay. So it's significant at 1%.
Continue.
Yeah, because when you, just referring to where you have highlighted also, you consider 3 star when P is less than 0.01, and looking at the complement C up there, we can see that the value for the complement, it's 3 star, negative 0.105 with 3 stars. And so we can conclude that it is at 1%.
That is complement, right?
Yes.
Very good. Who doesn't understand? What can you say about the significance level for income? Income. Still using the model 1. Significance level for income. M. Income is represented by M. Is it significant or insignificant? Income. Nelson.
Yeah, Prof, it's not significant because there's no star associated with it.
Okay. Very good. Now, what do you think is the thing in the parentheses? What is that thing in the parentheses?
Which one? Here in the bracket. 0.75.
Like that. What is the star? What is the
one in the bracket?
The one in the bracket. What does it mean? Raise your hand. Raise your hand. And mute yourself if you are not talking. Yeah, Richard.
Is R square.
What is R square? Oh, no, it's not. We don't have R square for each independent variable. It's not R square. I explained it the last time. Richard, you understand? You don't know the thing in the parentheses. So there are, first of all, usually there are two possibilities. The standard error, but basically it's a standard error. So just to give you a clue, because we are comparing tables, when you go here, when you go to the original result we had, check for price, you see that the standard error is 1.57. 1.57. That is a standard error. And the T statistic is 2.1. So we always put the standard error in a bracket. Sometimes some people are bold and then they'll put the T statistic rather in the bracket. No. The standard, why? Because when you divide every standard error by every T statistics, every estimate, every coefficient divided by the standard error, that will give you the T value. Write it down. You forget. The estimate divided by the standard error will give you the T statistic. So sometimes in an exam, I can rather give you the T statistic and I'll tell you, or I'll give you the estimate and the standard error, then I'll tell you to find the T statistic. Okay. Now let's go down and see that bracket for price is the same 1.57. So that is the standard error you have in the bracket. Okay, let's look at location, religion Muslim. Is it significant or insignificant? Religion Muslim. Religion Muslim, when you see it, it has 3 stars. So what does that tell you about the importance of that variable? If you check it very carefully. Can you raise your hand and let me identify the person? Yes, Richard.
Yeah, okay, so Doug is telling us that religion, Muslim is significant. Statistically is significant.
It is significant. Who is having OW lecture? All right.
I think that Muslim, though it shows 3 stars, we know that Muslim is a dummy variable and therefore it's insignificant.
It's not because it's a dummy variable that is determined. It's because that is the value it will get in the particular data we have. That's right. So what I'm just wanting to know is that you can use the stars to determine at what level of significance the value is. Very good. Let's go to the next part. So I gave an example here. The estimate of price of complement is significant because the p-value of 1% is less than the 5% alpha level. So you can use this approach. Even you can use a confidence interval to determine the significance of every variable. Okay. The next question is, are the coefficients jointly significant? What does that mean? Are the coefficients jointly significant? What does that mean? You can explain. the coefficients are jointly significant means that you are being asked whether collectively they combine their forces and powers together so they eventually become significant. So are they together important? What will you use to check this? What here will you use to check that result? Yeah. You can use some information there to check the result. Or you can go up here. The original graph that we had, which is this one. Yes. So you can use this information here. But there's something in there you can use to determine if they are jointly significant. You can tell us. So this is a value there. The F statistic, the 31 degrees of freedom, the p-value is 0. So you can see that the F statistic is 329.1. The p-value is 0, 0, 0, which means that collectively there is no mistake in using that value. Therefore, you can conclude that religion, is it religion we are looking at? Collectively, you can conclude that jointly they are all significant put together. That's how you determine the joint significance of all. Now we get to interpretation of the results. When you are interpreting, you got to use all the energy you have. You got to know all the variables. And you have to know what you are interpreting. What we are going to do is that we're going to interpret one particular number. Interpret one particular religion. So, price. Who can interpret price for us? What is the coefficient of price? Yeah, anybody? First of all, when you check the coefficient of price, you will see that it's 3.5, but it's negative. It's 3.5 and negative. That's it there. So when you check the coefficient, how will you interpret that negative 3.5? How will you interpret it? Emily?
Okay, Doc, so I would say an additional increase in price leads to 3.5 decrease in quantity demanded, holding all other things constant, all other factors constant.
What are all these other factors?
Okay, so holding the income, the complement price, the location, urban, occupation, teaching, occupation, trading, religion, Christian, and then religion, Muslim constant.
Very good. Guys, do you understand? That's how you interpret it. Now, let's go to the dummy, which is Muslim. When you're interpreting Muslim, because it's not rising or falling, it's a dummy, static. How would you interpret that? Now, let me see the smart ones among. How will you interpret religion?
Look, let me
Why?
like
Yes.
so holding all other factors constant, the quantity of money is likely to increased by 15.5548 if a person is a Christian than a Muslim.
If the person is what?
If a person is a Christian
And a Muslim, right?
yes, please.
You are interpreting Muslim, so that's all. Who can interpret the coefficient for Muslim? You see, the coefficient for Muslim is -23. On average, given the price and complement price of gin, location of the shop, occupation and religion of the occupation and location. Let me start. On average, given the price and complement price of gin, income of the people, location of the shop, and occupation of the people, quantity demanded is predicted to be 23.3 units less if the people are Muslims than Buddhists. Buddhist is not here. And that is the more reason why Buddhist is the reference category. Before you interpret any dummy variable, you got to know the reference category for that dummy. If it is marital status and they have taken the widowed as the reference, everybody will be analyzing from that point of view. So take note, when you're interpreting this kind of variables, dummy, you don't interpret them as a 1 unit increase in that, 1 unit increase in that, 1 unit. No. So that is how you got to tackle interpretation. By the way, all that we did, and your slice it. Okay. Now, partial significance, we've done it, and interpretation with brackets. We go to another statistic that we use to determine the fitness of the regression model. This is known as the R square, the RSS over the TSS. The R square is a percentage of the total variability in Y. That is the R square. It tells you how good your model is. If your model is bad, the value is smaller. Good, bigger. How bad, how good is irrelevant. The R square tells you. But adjusted R square tells you information that the R square doesn't tell you. What the adjusted R square does is that it adjusts the R square by introducing a power model. And then you see that the R square is always, the R square is good, but then the adjusted R square penalizes the inclusion of irrelevant variable. The adjusted R square, it penalizes you including irrelevant variables in the model. Both of them are between 0 and 1. Now let's go back to our own. Is our regression model well fit? Who can tell us? Our regression model, is it well fit? Hello? Yeah.
Look, we are still seeing the PDF.
Yes. Can we see the model?
But I wanted you to see that because the moment I go there, it means that I'm not letting you think. I wanted you to tell me before. Yeah, Richard. Yeah, Richard, go ahead.
Doc, I'm trying to, yeah. Okay, so now, Doc, please, can you hear me?
Loud and clear.
Okay. So, looking at the model, the R square, I'm looking at the R square, and the R square is good. So, meaning it is.
Okay, who is serving there? Yes, let me do 10 minutes.
Okay, Doc, I think we can say that the model is well fit because the R square is 90, almost 99%, which is over the 50%. That's a requirement. So since it's greater than 50%, then the model is well fit.
What is the value?
It's 0.988.
So that is how you interpret R and the R square. They are very, very useful. Okay, so what does it mean when the R square equals the adjusted R square? What would that mean? Mariam.
That means there are no irrelevant variables in the model.
Excellent. That's it. That is how you examine. If you were to interpret the value of the R square, the 99%, what would that mean? What would that imply? Yes, Mara.
About 99% of the variable explains the model, so it's well fit. The viability of the model.
Okay. Jerry.
Doc, so 99% of the 99 of the model is explained by the independent variable.
What is that? What you said sounds like Chinese.
That's it again.
Yeah.
So about 99% of variability of the dependent variable is explained by the independent variables.
Very good. Richard, is your hand still up?
Yes, but you called Jerry.
So 99% of the changes in the quantity demanded of gene bitters has been explained by all the independent factors. That is how you interpret it, understand it. R square is not the only one. MSE, and how to estimate it in R, and the result for our data. Root MSE.
What should I do?
So the first one took the square. This one doesn't take the square, but the square root. It helps to get the metric in the same unit of measure. So, but note that you can compare the MSE and the MS, the other MS, you can compare each one of them and see which one is better. Root mean squared error is usually better than the R square. That's your okay. So you can calculate all of these things in R. I didn't want to bore you with the same thing in Python. So remember our results here again, and then let's finish up by specifying the regression model. If you were to specify the model, you are bringing only letters and numbers. I want you all to specify the regression model for me. When you finish specifying, you can take a picture Then you put it on the groupage. Take a picture and put it on the groupage. You will have something like this in this answer.
Doc, please, can you come again?
With what?
First, what you just said. I just said take a picture, but I didn't hear what preceded it.
Write the estimated, the specified regression model. You're answering this question on the screen. How you write it, Mike?
Doc, please, you've gone away from the page.
Sure.
Hello, Doc. Okay,
Yeah.
thank you.
Okay. Right. Nobody has documented the results on the page. Okay, so who is York?
Doc, please, I'm the one.
Joseph?
Pardon?
Okay, Joseph. The two of you have done that. So I'll level the playing field. Yeah, you are wrong. Joseph, you are correct. Emily, you are wrong. So only one of you is correct, and that's it. I end that one. And that was Joseph. So Joseph, that's 3 marks for you. I already have some marks for some people, but for this one.
Oh, Dog, this one we are about to post our.
Joseph, did you get that? So give your mark to Emily.
Sure, dog.
Doc, please come again.
I said that for this very one, only Joseph had a mark of 3.
Okay.
So look at the question carefully. The question says specify the model, not write the estimated equation. The specification of the model requires that you are bringing in the data parameters. The writing, so this is the answer. This is the way it's got to be. You cannot write it like estimated regression equation. Now, the question was saying specify the model.
Okay.
So that's it. Next question. Write the estimated regression equation. I'm sure that's the one that the two of you did. The estimated regression equation requires you to only replace the data parameters, as you can see. Any question on that? Good. Now, we go to the next part. And that next part, and there's a last part, is prediction. Your model can be validated, and once that is done, you can use it to predict the quantity demanded of gene vectors, given any of the other variables. If you take the log of the dependent variable, you got to be careful, because if you're going to do prediction, you need to transform the value back to the original scale on the log scale. So that converting it back is very important. Sometimes you have to do this by inverse of log transformation, which is the exponentiation. So now let's look at a question related to prediction. There are 2 things regression is used for. 1, for establishing causality. 2, for predicting. Before you can predict, you got to know the existing things. So we want to predict the quantity demanded of gene vectors made by some Muslim traders in an urban town. Compare that with the quantity demanded of gene vectors made by some Buddhist fishers in a rural area. Given that in both cases, gene vectors is costing 50. Computer is costing 50. The average real income of the customers is 20. Don't look at how hard or how easy it is. How do you do the prediction? First thing you got to do is to write the equation. Now, so look at it. In both cases, what are the same? In both cases, what are the things that both of them are purchasing the same price? So how do you go about it? In both cases, the first thing you got to do is to write your equation. So this is the equation. I've deliberately decided to use a different equation, but the principle is the same. And this, I've just used acronym, but when it comes here, it's the same thing that we are using here. The same thing here. So you're going to fit in the value for price. What was the value for price, guys? What's the value for price that was mentioned? So use an estimated equation. What's the value for price?
15.
15. So the first thing you're going to do is to put 15 here. What about complement price?
15.
Also 15.
What about income?
20.
20. So whatever you see, you put 20 there. But then you were told that in the first scenario, the people were what? Look at it. Made by Muslim traders in an urban. Muslims in an urban. Muslim traders. Okay. So when you in an urban town, so log urban will be what?
Block 1.
1, because this is a dummy. You are either in an urban or in a rural. So to be the value of 5.11 times 1. What will be the value for occupation teaching?
Mm. 0.
Good. Because there is no what? Teachers. These people were
they were
traders. That's the first scenario. Now, let's go to occupation trading. What will be the value?
One.
Religion, Christian. So you put
0.
0.
We are talking about.
So you put 1. The religion Christian is 0 because the people are Muslims. And then religion Muslim is what?
1.
That's it. At this stage, you can just simplify and then multiply it through and then get a number. So when you do that, you're going to get a very simple number, which is this. That's it. That's the first scenario. In the second scenario, you were told, watch it. See, you're comparing. It says that Muslim traders in an urban town, compare that to that of the quantity demanded made by Buddhist fishers in the local area. Buddhist fishers. As for the 15, 15, 20, we are going to have it. But these are Buddhist fishers. So, watch it. So we are looking at Buddhist fishers in the rural area. So what to be the value of course, if we were to substitute them here, we're going to get 15, 15, 20. What to be the value of location urban? The value of location urban. Remember, these people are in a rural area, so that would be 0. What about occupation teaching?
0.
Very good.
Are you muted? Okay. You should unmute.
Religion Christian?
0.
0.
Religion Muslim?
0.
0.
So whatever value that is in the last 4 are useless. They will all vanish. The people that will be recognized, or those items that will be recognized, are those that are underlying or cancelled. So when you do that, okay, you're going to get a value for that as well. So once you get this value, compare which one is more. Okay, so if you look at the second scenario, it was 216, 211. The first scenario is 136. Combined, you can see that the second scenario is 74.8 more than the first scenario. What was driving the difference? Because they had the same 15, the same that, the same that. But what was driving the difference? Something was driving the difference, wasn't it? What was it?
Religion.
Yes. These three, categories were driving the difference. That is what was causing the difference. That's it. That's how you execute prediction. Next time, we're going to look at the diagnostics. But that is exactly how you do regression prediction with the causality. Benjamin, that brings us to the end of the entire tableau. Any questions so far? Any questions?